Hello everyone. Today we are here to talk about the 2014 Physics Nobel Prize, which was awarded to our three scientists, Akasaki, Amano and Nakamura. Okay. So we'll talk about why they won the Nobel Prize, what was their impact in an interactive sort of a format. Okay. So as we all know, to win a Nobel Prize, it's not enough to just have a scientific breakthrough. There also needs to be some large impact on humanity, on human knowledge, which makes the prize viable, right. So if we look at the Nobel Prize citation, it says that it was awarded to these three scientists for the invention of the blue LED, which resulted in the production of white light sources. Okay, so the connection is important. What they invented was a blue LED which allowed the creation of a white light source, right. So a little bit of color theory will help us understand how this works. So here is a artist's color wheel, which all of you have seen while growing up, and it shows how different colors mix to produce yet new colors. So if I look at the schematic of the colors over here, it shows the three primary colors. So there is red, green and blue, right. Now
why only these three colors?
So red, green and blue are considered primary colors. If we mix these colors in different proportions, we can generate any other color. So it's sufficient to have three. You can use more, but three is sufficient. 3 is the minimum requirement. Okay. So when we talk about red light sources or green light sources, efficient sources for these existed for a long time. So like red LEDs were produced in the 1960s, green LEDs came about in the 70s, but for a long time efficient blue light sources were not available. So if you look at just red and green, as you can see in the color wheel, when I mix them, at best I can get yellow or different shades of red, different shades of green. White remained elusive because there was no blue light source. So you can see that there are two possible ways in which I can get a white light. Either I can combine red, green and blue that produces white, which you can see at the very center, or another possible combination is if I take blue and combine it with yellow, right. Between these two possibilities, obviously the one that would be cheaper would be the one with blue plus yellow, right, because there I would be able to accomplish this using just one LED, as opposed to the other option where I need three light sources, right. So one of our prize winners, Nakamura, he actually worked at a company. The name of the company was Nichia, and they were in the business of making light sources. So from the very beginning, they had in mind a commercial angle, that whatever product we make, we should be able to commercialize it. This is unlike many of the motivations in the scientific community where they bring it to the proof of concept level and then leave it, right.
So I have a question. Why we cannot make a white LED directly? I mean, why we need a
combination? Yeah. Okay, so that's a good question. So white, if you think about it, is not a pure color. It does not have a wavelength. White is the illusion that the brain creates when green, red and blue combine in equal amounts, or blue and yellow combine, right. So white light by itself is, as I mentioned, it's an illusion which the brain constructs in response to seeing various colors coming together.
Okay, means there is no actually white color.
There is no white color, there is no wavelength or frequency you can associate with white color. It's a mix of everything that creates the perception of white. Okay. So that's why we need to mix blue with something, right. So in Nichia, what they did was they took a blue LED. So an LED is our building block of light, a light emitting diode. So they took this blue LED, it produced blue light, and they coated the screen of the bulb with a yellow chemical called phosphor. Okay. So we won't go too much into the details of what phosphor is, it's a complicated chemistry in itself, but it has a very elegant and simple property. It absorbs blue light and it emits yellow light in return. So now you imagine that there is this, as this diagram shows, there is a blue LED sitting inside a bulb holder and the casing is covered with this yellow phosphor. When these two mix, the yellow light produced by the phosphor and the existing blue light of the LED, these two combine and produce white light. So if you go out into the market and buy a white LED, if you open it up, what you will find is one of two things. Either the casing of the bulb has the phosphor coated inside it, or you will find a blue LED with plastic panels that are encasing the blue LED, and these plastic panels contain the phosphor inside it. Okay, so this is an idea which Nichia came up with in the 90s, and over the last 2 decades they improved the efficiency to such a point that you can actually go and buy it in your local hardware store.
Okay. So is there any other application of this invention, or just a room lighting or something?
Yes, so room lighting is the most obvious invention that we think of, because when we are surrounded by, say, white tube lights and so on. So when we can replace them, of course it's a good thing. But there are applications of white light sources that go beyond lighting. So I'll cover these briefly. There's of course the lighting which I spoke about, which is in the top left of this graph. By not converting it to white but just keeping it as blue, you can achieve all sorts of decorative lighting. You can see that it's a common sight these days in New Year functions and so on and so forth. Automobile lighting also, in headlamps you are beginning to see these very bright headlamps which improve the visibility at night. Agriculture is another interesting application. Many places where you want to control the amount of light that plants are getting to grow, they need actually a white light source to simulate as best as possible what the sun is giving to them. So this is particularly useful in those parts of the world which are very high in latitude or very low in latitude, where the amount of daylight that plants are getting is limited and you want to grow plants in a greenhouse. So that's your agriculture. Indoor lighting, of course, we have seen, and one of the most biggest applications with commercial impact is displays. So whether you look at your iPhones, you look at your LED TVs or your computer screens, the availability of cheap and energy efficient white light makes it possible to bring down the cost and improve the life of every device that comes into contact with it. Okay. So this is sort of an overview of where all we can see white LEDs or blue LEDs rather fitting into the picture. Now let's try to quantify a little bit in numbers what is the impact on humanity. Okay. So I'll talk about the first aspect. Why is this a big deal? We will talk about efficiency. So the very first light source that mankind used was the incandescent bulb. Right? Everyone has seen that incandescent bulb. We've been using it for more than 100 years. The basic principle is you run electricity through a wire, the wire heats up, and in turn this heating produces light. Right? Let's assume that 100 units of power are going into this bulb. Only 4 units of that gets converted to light. So it's a pretty inefficient system. A recent invention were the fluorescent or the compact fluorescent lights, or we call them CFLs. They improved the efficiency a little bit. So now they converted 12 units into light. So I given 100 units of power, out comes 12 units of light. The reason why the LEDs are such a game changer is because they brought this efficiency up all the way to 50%. So if I send in 100 units of power, half of them are converted to light, right? So what that means is one LED can replace 4 CFL bulbs or 12 incandescent bulbs. So imagine you're already saving so much in terms of cost. In a room which needed, let's say, 12 bulbs, you can go in and put one LED. Right? So you can imagine what kind of savings in cost will be there. So cost is one saving. What else is it saving on? That brings me to the second aspect of why is it a big deal, and that is life. What is the lifespan of these devices? So this graph shows the lifespan in hours. So if I take a regular bulb, your incandescent bulb, it has a life of about 1000 hours, right? The CFLs do 10 times better, so 10,000 hours, and LEDs do 10 times even better. So if I look at the comparative sort of relation between these, I would need to replace a CFL bulb 10 times more frequently than an LED, and I would need to replace a regular incandescent bulb 100 times more frequently than a LED, right? So again, what I am saving is in terms of lifespan and cost. Okay.
So I have one question. So in last slide we talked about the efficiency of the 3 things. So can we somehow improve the efficiency of LED more? I mean, on what factors the efficiency depends?
Right. So the efficiency depends. If you want to understand how the efficiency came to a commercializable point in the first place, we need to understand what is this LED that we have been continuously talking about, what does it mean, how does it work, and actually the scientific story of the Nobel Prize lies in understanding what were the key innovations that helped to bring this thing to the market, right? So what is an LED? So as I mentioned, an LED stands for a light emitting diode. Okay. A light emitting diode is based on the idea of a what is called a p-n junction. Now I will explain what a p-n junction means. Before that, I must tell you what a semiconductor is. We know what a conductor is. For example, if you touch a piece of wire that is connected to the electrical supply, we all know what happens. We get a shock. And why do we get a shock? It's because the conductor, I mean the electrical wire, it's a good conductor of electricity. It passes electricity right through us. Whereas if we touch that same wire with a piece of wood, no electricity flows, because wood is a bad conductor of electricity. Now there are compounds whose conductivity lies in between these two, and we call them, the name is self-explanatory, it's a semiconductor, right. So almost all of modern electronics are based on semiconductors, because you can control the conductivity of these materials in a nice way, and by doing that you can make various sorts of devices. So what is a p-n junction? What is a p-n junction, right? So the first step is what is called the substrate. Now what is a substrate? A semiconductor is not some material that you can go and dig from an ore, right? It is something that you have to create artificially and in the laboratory, okay. So because of that, I can't start with like a block of impure gold and keep purifying it and end result being gold. I have to create this very high quality material step by step, atomic layer by atomic layer. So I need some sort of starting seed base on which I will do it. It's like when I go to make a building, I just don't start piling bricks on the ground. I need to first dig a foundation. So I need a foundation of that material itself. So that's called the substrate. The next step is I need to put a layer of what is called an n-type semiconductor. An n-type semiconductor simply is a semiconductor which has an excess of electrons as their charge carriers. I need to conduct electricity, and to conduct electricity there are two sorts of charge carriers. One can be negatively charged and the second can be positively charged. So I have an n-type layer which is negatively which has negatively charged carriers. The third step is the p-type layer which has positively charged layers. So all very well. The next thing I need to do is send electricity through this. So I connect it all to a battery. What does the battery do? It will send a current of electrons from the negative terminal. Electrons we know are negatively charged, they are attracted to the positive terminal of the battery. So they are in a rush to get from the negative to the positive through our little device. Now as these electrons enter the device, the n-type charge carriers, they are attracted to the p-type charge carriers. In the middle, in this junction region, is where the negative and the positive charge carriers, they combine, and in the process of combination they give out light. So if you are doing it in the lab, the moment you turn a circuit on, you will observe some light that is coming out of it. So that brings us to
question. So we talked about what is the LED, right?
Right.
So previously we talked about red, yellow and blue.
Right.
So what factors here will decide that we have a red LED?
Very good question. So what you are asking is what determines what is the color of the light, in other words, that is coming out of this device, or is it fixed, right? So this is one of the main reasons to use a semiconductor, that you can engineer, you can change what color comes out of it. What color comes out of a semiconductor depends on a very intrinsic property of this semiconductor called the band gap. So band gap tells us what is the color of the light that comes out. Something that has a very high band gap produces a very high energy light. High energy means blue light, okay, because energy is proportional to frequency, which is inversely proportional to wavelength, right. So blue light will come out of a very high energy band gap, and red light on the other hand, red we know has the largest wavelength, therefore the smallest frequency, therefore the least energy, right. So that's how we get light, and as I just mentioned, that the color of light depends on the band gap, right.
Sir, one question.
Yeah.
Why we could not use triode here?
You mean why not use a combination of
Triode, because the efficiency of triode is very much high than diode.
So the triode will perform a different function. A triode will perform the function of a transistor, okay, which is not what we are exactly interested. A triode, I can think of a triode as made of two p-n junctions.
Yes.
I am not interested in making a transistor or some sort of a logical circuit out of it, which is where the triode would be helpful. I am interested in simply having these p-type carriers and n-type carriers combined to produce light. Okay. So let me solve a simpler problem first. If I can make it in a diode, then maybe I can think about the triode, or maybe not. If I can do good enough with the diode, I need not worry about the triode. So we will see how that plays out. Okay. So as I mentioned at the very starting, red and green light sources existed from the 60s and 70s. So the challenge was about blue LEDs. So people looked around, what are the semiconductors that have a band gap that can give blue light, right? So there were two candidates for blue light. One was a material called zinc selenide, which was grown on a substrate. As I mentioned, the first step was a substrate. So the substrate was yet another semiconductor called gallium arsenide. And the second candidate was something called gallium nitride. It was grown on a substrate of sapphire, right? At the time when our prize winners entered the scene, there was the situation was that zinc selenide was a very promising material. Why? Because they were able to grow very high quality and high purity material, and whereas gallium nitride was like the underdog. No one really bothered much about this material because it had very poor quality. People were not able to grow a high quality gallium nitride crystal, so people did not spend much time on it. Now Nakamura mentions this in his Nobel Prize lecture, that in the late 80s he had just graduated with a master's degree, and he had gone to the United States, he had gone to the University of Florida, and he wanted to work on semiconductor devices. And what happened when he went to the United States is that people asked him, so do you have a PhD degree? He said no. Do you have any papers? He said no. Then said, okay, then you can be a technician for our equipment. So Nakamura was not very happy with this arrangement. You know, he thought that these guys will do all the science, they'll write the papers and the patents, and what about me? I won't even get mentioned. So it must be mentioned. I must say at this point that Nakamura, one of his main motivations in life, you will find it surprising, he wanted to get a PhD. That was his end goal in life. He just wanted a PhD. And at that time in Japan, they had a scheme where if anybody wrote 5 papers, they would be given a PhD degree. It was called a paper PhD. So Nakamura, in his ingenious way, thought, see, 5 papers is what I need. I need to do those things that will get me those 5 papers as soon as possible. So he realized that my story is not going to work out in the University of Florida. So he went back to Japan, he joined a company, and in the company he managed to convince them that we need to produce these, we need to work on blue LED sources, right? And so he went to these scientific conventions within Japan, and there was a very funny story that there were about 500 people at the conference who were interested in zinc selenide. As I mentioned, very high quality. So everyone thought, yeah, zinc selenide is the future, let's work on it. Whereas there were less than 10 people who were interested in gallium nitride. Not surprisingly, all 3 of our prize winners were in that conference room which had less than 10 people, and they were interested in gallium nitride. Now gallium nitride, why did Nakamura choose gallium nitride? He thought that if there is a field where there are 500 people, what are the chances of me with a master's degree and no papers of doing anything? So he said, I think my chances would be best if I go into this place which has 10 people. If I do something, I at least may be able to get a paper out of it. He was not thinking about Nobel Prize, far from it, right? And the other 2 prize winners, Akasaki and Amano, they had different motivations for choosing gallium nitride. They thought that gallium nitride had a problem of growth, but it had other properties which they could harness if they were able to overcome this growth challenge. They had invested greatly in laboratory equipment which could produce gallium nitride, and in the scientific community that's a big investment. It's not that today I decide to work on zinc selenide and I can start working on it and abandon the rest of my equipment. It costs millions of dollars to set up a reactor to produce one sort of crystal. So these guys were committed to gallium nitride and they were working on this. And so the year is about 1989 when Nakamura came back from the United States and started working on gallium nitride. He convinced his company to invest $2 million to buy a reactor, so pretty persuasive person, and they started working on gallium nitride. Okay. So let me show you the sort of challenge that these guys were up against. The analogy I gave earlier was of laying a foundation for a building, right? So if I want to lay a, let's say a a building, I start by putting down the foundation, and then in that I erect these pillars of concrete and iron bars. We have all seen those, and on top of that we build it. Now supposing I want to build something which has a certain dimensions. In this case, that dimension is the spacing between the atoms. So if I take zinc selenide, I am interested in what is the distance between the zinc and the selenium atoms, and I want that to match the foundation. So you can see that gallium arsenide, which already existed, and zinc selenide had almost no mismatch. So what happened is that it could very nicely grow on top of it, and you would get a very high quality material. What was the case with our other candidate, gallium nitride? A big mismatch, almost a 16% mismatch. So it's like trying to build a building where everything is mismatched. So you will not be able to get enough strength. As you start piling on the layers one after the other, because of this mismatch at the very foundation, one small earthquake and the building will fall, right. So that's precisely what was happening with gallium nitride, which is why it was a challenge, which is why of those 510 people, 500 worked on zinc selenide, right. So this is the result of growth on the lattice mismatched gallium nitride. You can see it's not a smooth material. There are these vertical lines all over, which are as a result of this mismatch in the dimensions over there. So if you produce any light in this structure, it's going to be immediately absorbed or scattered off by all these random sorts of vertical lines, right. So this is the reason why people had given up hope on gallium nitride altogether, and that's when the heroes of our story started their innovations, okay. So the two groups had two different strategies to use. So our first group of Akasaki and Amano, what they did is they started with the conventional crystal growth. So here this graph shows gallium nitride, which is the white colored material, it's the top view, and the darkish thing is sapphire. As I mentioned, because of this lattice mismatch, what would happen? Instead of getting a smooth homogeneous layer, things would clump up, and you would have these sorts of islands. Instead of a smooth layer, you would have these islands of gallium nitride, which would be no good. And through a sort of series of interesting almost mistakes in the lab, what happened is that in the process of growth, Amano realized that he had not set the temperature correctly during the growth. So temperature is a very important parameter when you grow these things, and for some reason he had managed to put a lower temperature than necessary, and because of that what happened is that the growth conditions changed. He also introduced a little bit of aluminum into the reaction, and so what happened is that in 1985 he grew what is called a low temperature buffer. So LT stands for low temperature. So it's this small little low temperature buffer here between the sapphire and the gallium nitride, which was grown at low temperature, which allowed the subsequent gallium nitride layers to be matched in the lattice constant much better. So you can see the dramatic difference on the right hand side. From these islands of gallium nitride, you have gone to a smooth layer of gallium nitride, okay. So they were able to overcome this growth challenge quite shortly, right. By the late 80s they were able to overcome the growth challenge. Meanwhile our other prize winner Nakamura, he had a different strategy, okay. Now I must mention that in this reactor people usually do not like to introduce aluminum. So if you notice that the buffer has aluminum in it, it's a alloy of, it's a compound called aluminum nitride, and people do not like to introduce aluminum into their buffer, into their growth chambers, because it messes it up, it leaves a lot of impurity inside it, okay. So Nakamura was convinced that this alone is not going to solve our problem. I will produce material which has some impurity. So he said, let me try to think of some way by which I can eliminate aluminum also from it, right. So this, I will just quickly show this picture. This is the first blue LED that our scientist Amano was able to show. It's a very small little graph over here. It's a PN junction that's glowing in the blue. So this was 1989, late 80s people had managed to show proof of concept, okay. Proof of concept meaning it works. Can I take this to a company and make a product out of it? No way, okay. And that's why Nakamura's invention was very important, and he was coming from the context of a commercial company who was always looking at how can I commercialize this. So Nakamura's challenge was to take this reactor. So this is a sort of schematic of the reactor. We won't go into the details, it's quite complicated, but this reactor accomplishes growth of whatever it is that you're interested in, gallium nitride, zinc selenide, whatever, in a very controllable way. He modified it in a very clever way where he played around with the temperature settings, and he was able to achieve a very high quality growth, all the time avoiding aluminum. Okay. So the story so far is that all three prize winners contributed in different ways to produce high quality gallium nitride. Having obtained high quality gallium nitride, they were able to produce a blue LED. Okay. But like I mentioned, that's not good enough. So that takes us to the next step, which is of improving efficiency. If I can make this blue LED to be brighter for the same amount of power that I am putting in, then I can maybe put it into my laser pointer and do all sorts of things with it. So this was the idea in the early 90s that was floating around, what we already discussed so far, which is called a homojunction. A homojunction is a junction made of the same kind of material. I took gallium nitride, I did some chemical change to it, I made a p-type layer out of it, I did a different chemical change, I made an n-type layer, right. So I have a p-n junction, and in the region where the p and the n combine is where these electrons and the positive charge carriers, they recombine and produce light. So this was the story so far. It required yet another Nobel Prize in physics in the year 2000 to unleash the next revolution, and that revolution was to improve the efficiency by changing this p-n junction just a little bit. So what they did is they introduced what is called a double heterojunction. So a double heterojunction, it's a separate lecture in itself, what is a double heterojunction, but for our purposes what it did was that it improved the efficiency a lot. And how did it do it? It confined the electrons and the holes to just one part of the junction, right. By confining them to one region, the efficiency improved a lot, because the light did not get scattered or absorbed in the various defects that the crystal may have. It was confined to one place, the process was far more efficient, and this is what made the efficiency really shoot up. Okay. And by the mid 90s, the company that Nakamura worked in, Nichia, was able to put out a press release saying we have managed to make a commercially viable blue LED, and the effect that this had on the competition, by competition I mean zinc selenide, was phenomenal. So to give you an analogy, it's like this, that you have been working with floppy disk drives, right, which were used before most of you were even born, which had the capacity of what, 1.4 MB, and you are working with a floppy drive and someone comes and gives you a flash drive which has a capacity of 512 MB, and then suddenly you are left scratching your head, why am I using this floppy drive anymore? So that's exactly what happened to zinc selenide. It was a promising material, but the improvement in efficiency that our prize winners were able to bring to the table was so great that people just didn't bother about zinc selenide anymore. In fact, there was a group at North Carolina State University and a company in the US which were working on zinc selenide, and by mid 90s they had also demonstrated blue light sources in zinc selenide, but after Nichia came out with its inventions, they just shut shop and went on to do other things. Okay, so it's what is called a game-changing sort of innovation, right? So this sort of I'd like to summarize the key steps that went about in the invention of the blue LED. We started with, of course, the sapphire substrate. Both Akasaki and Amano and Nakamura came about with different ways of growing a high quality gallium nitride crystal. A lot of innovation was required to make a P junction and an N junction. This process was carried out through the 90s, and finally by introducing this double heterojunction layer, they were able to improve the efficiency a lot, right, which gave us our blue LED. So now let me tell you a little bit more about Nakamura's story and why it is so inspiring for students, particularly students, also for all other researchers. So as I mentioned, when he entered the scene, he was only interested in his 5 papers and his paper PhD, right. He had somehow managed to convince the company into investing $2 million into this reactor, but he also knew that the company did not have infinite patience. At some point in the near future, they would cut off his funding. So he set about this task with the motivation and the obsession of a madman, 7 a.m. he would be in his lab working out different ways of producing high quality gallium nitride. In the afternoon he would analyze his crystals, and day in day out he would go and he would keep doing this for about 2 years. He writes that he would barely talk much with his family. He would go home, have dinner, have a bath, go to sleep, next day repeat this, and he would just keep doing this. And that obsession is what took him through. And he had of course no idea that he's going to get a Nobel Prize out of it or anything. He was focused, right? It's like Arjun and the eye of the bird or fish or whatever, right? And the next sort of key point, which is for companies, is to have a little bit of foresight, that if you were to, for example, Nietzsche, before this guy invented anything great, if they were told that, oh, give us $2 million, this may improve your bottom line a few years down the line, most companies would not be willing to take the risk. But they took the risk and they changed the complete landscape of technology by doing that, right? So the idea that setting aside some part of money for pure R&D can be actually very, very beneficial, not just for themselves but for humanity on whole, right? And the commercial environment brings a lot of focus into products. So for example, if it were just proof of concept, people would have stopped at the demonstration of the homojunction blue LED. Yes, we have done it, we have written a great paper about it, let's move on to something else. End of story. We would not be having blue or white LEDs today, right? So it's taking an idea through to its logical conclusion, which is really an important lesson. And the funny story about Nakamura is that he finished most of his key work for which he won the Nobel Prize by the mid 90s, by which time he didn't even have a PhD. So he got his PhD at the age of 40 in 1994, and you know from the previous graphs that I showed you that most of his innovations were finished by the year 92, that is before he got his PhD degree. So it's not that everyone has to go through the hallowed halls of I don't know, IIT, MIT, whatever it is, and only then you can get a Nobel Prize. You need some amount of obsession and craziness and a faith in what you're doing, and that can sort of give you a lot of unpredictable stuff. And this is the sort of final slide with which I'd like to summarize, that what is the impact that these guys' ideas, what did they have on the world? By implementing the LED light sources for just lighting alone, you can save about 40% of your electricity bill, right? That's an estimate for the US by 2030. You eliminate the need for more than 31 gigawatt power plants. And if I convert these numbers into how much carbon dioxide do I save, it's a staggering 185 million tons of carbon dioxide that I save, right? All because one guy wanted a PhD.
So will the white light given by this LED?
Which LED?
The LED we are creating by using the blue LED.
Mm-hmm.
So will it give the all 7 spectrums if we pass it through a prism?
So good question. If I take the, let's say I have a blue, a green and a red LED which is combining to produce this white LED, right? Now this white, as I had mentioned earlier, is a perception of the brain, it's not a color in itself. If I pass this light through a prism, it will break up into its constituent light sources. So in this case it would be the blue, the green and the red. If it were the phosphorus screen sort of a light, I would get blue and yellow. Okay, I will not get all 7 colors. Okay. Thank you.